Treat energy availability as the primary factor when evaluating the viability of space-based data centers. One of the strongest arguments for moving computational infrastructure into orbit is access to nearly continuous solar power. Unlike ground-based facilities that must contend with weather, seasonal changes, and local grid constraints, orbital platforms can receive sunlight for extended periods. The practical lesson is that future designs should prioritize orbital locations that maximize solar exposure while minimizing eclipse durations. Every percentage increase in power availability directly improves computing output and reduces dependence on large energy storage systems. Cooling should be considered the defining engineering challenge rather than power generation. On Earth, data centers remove heat through air conditioning systems, liquid cooling loops, and environmental heat exchange. In space, there is no atmosphere to absorb excess heat. The only way to reject thermal energy is through radiation. This means thermal management systems become one of the largest and most important components of any orbital computing facility. Engineers should design computational hardware around heat rejection capabilities rather than attempting to adapt conventional terrestrial architectures without modification. High-efficiency processors, advanced heat pipes, liquid cooling networks, and large radiator arrays will likely determine the economic feasibility of space-based computing. Hardware selection must prioritize durability over peak performance. Terrestrial data centers can replace failed components quickly and inexpensively. Orbital facilities may operate thousands of kilometers away with limited maintenance opportunities. Radiation-hardened electronics, modular architectures, and fault-tolerant systems become essential. Every component should be designed with redundancy in mind because hardware failure is significantly more expensive when physical access is limited. Future orbital servers may sacrifice a small amount of performance in exchange for dramatically longer operational lifespans. Communication infrastructure deserves careful planning from the earliest design stages. A data center is only valuable if information can move efficiently between users and computing resources. Low Earth orbit offers reduced communication delays compared to more distant locations, making it attractive for applications that require responsive performance. However, orbital facilities require extensive ground station networks, relay satellites, or laser communication systems to maintain continuous connectivity. The most practical strategy may involve integrating data centers directly into future communication satellite constellations, allowing computing and networking infrastructure to evolve together. Focus first on workloads that naturally benefit from space deployment. Not every computing task needs to move off Earth. Applications involving massive scientific simulations, climate modeling, astronomical data processing, satellite image analysis, and artificial intelligence training may be particularly well suited. These workloads often consume enormous amounts of electricity and generate substantial heat. Relocating them to orbit could reduce pressure on terrestrial power grids while taking advantage of abundant solar energy. Latency-sensitive consumer applications, however, may remain more practical on Earth until communication technologies improve further. Design data storage systems around resilience rather than capacity alone. Space exposes electronics to radiation, charged particles, and occasional solar storms capable of corrupting stored information. Error correction systems, distributed backups, and autonomous recovery mechanisms should be integrated at every level. Rather than relying on a single orbital facility, future architectures may distribute data across multiple platforms operating in coordinated networks. This approach improves reliability, while reducing the consequences of individual hardware failures. Launch economics remain one of the most important practical considerations. Every kilogram delivered to orbit carries significant cost. Data center infrastructure must therefore be optimized for mass efficiency. Lightweight structural materials, compact server architectures, deployable radiators, and modular construction methods all contribute to lower deployment costs. Designers should constantly evaluate whether a component justifies its launch mass through measurable improvements in performance, reliability, or operational lifespan. Autonomous maintenance capabilities will likely determine long-term success. Traditional data centers rely on human technicians for repairs, upgrades, and troubleshooting. Orbital facilities must increasingly handle these tasks independently. Artificial intelligence systems capable of monitoring hardware health, reallocating workloads, diagnosing failures, and initiating corrective actions become essential operational tools. Robotic servicing systems may eventually perform component replacement and upgrades without requiring human astronauts. Cybersecurity becomes even more critical when infrastructure operates beyond direct physical control. Space-based data centers may host valuable scientific information, government systems, financial services, or artificial intelligence platforms. Security architecture should be built around multiple layers of protection, including encryption, hardware isolation, secure communication channels, and autonomous threat detection systems. The inability to physically inspect hardware on demand means digital security measures must compensate for reduced physical oversight. Orbital debris represents a unique operational risk that terrestrial facilities never face. Even small fragments traveling at orbital velocities can damage critical infrastructure. Data center platforms should incorporate protective shielding, collision avoidance systems, and continuous tracking capabilities. Choosing orbital locations with lower debris density may slightly reduce accessibility but significantly improve long-term survivability. Environmental sustainability is one of the most compelling long-term advantages of space-based computing. Conventional data centers consume substantial amounts of electricity and water while contributing to local heat generation. Orbital systems could potentially reduce pressure on terrestrial resources by generating their own power and rejecting heat directly into space. However, sustainability calculations must include launch emissions, manufacturing impacts, and end-of-life disposal strategies. Responsible planning requires evaluating the entire life cycle of the infrastructure rather than focusing solely on operational benefits. Modular construction offers one of the most practical pathways toward scalability. Instead of launching enormous monolithic facilities, operators can deploy smaller units that connect into larger orbital computing networks over time. This approach reduces initial investment risks while allowing gradual expansion as demand grows. Standardized interfaces for power, cooling, communication, and data transfer would make future upgrades significantly easier. Consider the potential integration between space-based data centers and other orbital industries. Satellite constellations generate enormous quantities of observational data that often require immediate processing. Space telescopes, Earth observation platforms, and scientific missions could benefit from nearby computational resources capable of analyzing information before transmission to Earth. Processing data closer to its source reduces communication requirements and enables faster decision-making. Artificial intelligence development may become one of the strongest drivers of orbital computing. Training advanced machine learning models requires immense computational power and energy consumption. As global demand for AI infrastructure continues to grow, terrestrial power grids may face increasing strain. Space-based facilities powered primarily by solar energy could provide a complementary source of large-scale computational capacity. Organizations exploring future AI deployments should monitor orbital computing developments closely because they may eventually influence the economics of large-scale model training. Manufacturing technologies will play a critical role in reducing costs. The most efficient future systems may not be fully constructed on Earth. Instead, they could be assembled, expanded, or partially manufactured in orbit using robotic systems. In space, manufacturing allows larger structures than conventional rocket fairings can accommodate and may eventually enable the construction of enormous radiator arrays or solar power systems optimized specifically for computing operations. Regulatory frameworks require as much attention as technical design. Data sovereignty, jurisdiction, privacy laws, cybersecurity standards, and orbital resource management become increasingly complex when computing infrastructure exists outside traditional national boundaries. Organizations considering future space-based computing investments should closely monitor international policy developments and actively participate in discussions shaping these emerging legal frameworks. Reliability metrics should account for unique space conditions rather than relying solely on terrestrial benchmarks. Solar storms, radiation events, orbital mechanics, communication interruptions, and servicing limitations create operational realities that differ significantly from Earth-based facilities. Performance assessments must therefore incorporate environmental resilience alongside conventional measurements such as uptime, throughput, and energy efficiency. Economic models should focus on long-term operational value rather than immediate cost parity with terrestrial facilities. Early orbital data centers will almost certainly be more expensive to deploy than traditional alternatives. Their advantages emerge through energy independence, scalability, reduced environmental constraints, access to continuous solar power, and integration with future space infrastructure. Evaluating these systems requires a strategic perspective that considers decades of technological advancement rather than short-term deployment costs. Future orbital computing networks may ultimately function as critical infrastructure for an increasingly space-enabled civilization. As satellite constellations expand, lunar operations mature, and deep space exploration generates larger volumes of data, demand for distributed off-world computing resources will continue growing. Organizations studying the field today should focus not only on current technical limitations but also on how advances in launch systems, robotics, energy management, communications, and autonomous operations could reshape the economics of computing itself. The most valuable insight is that space-based data centers should not be viewed merely as terrestrial facilities moved into orbit, but as an entirely new category of infrastructure designed around the unique opportunities and constraints of the space environment.